Okay, let's run come on, the magic school bus. Sea llamas go projectiles! Okay, so what we're going to look at here, we are going to look at a Unit 5C2 problem. This is launching a object, whatever it is, at some angle. Now when we do these problems, we are traditionally going to do them, for simplicity, on flat level ground. Okay. And the reason we actually do this is you can do this problem going from level ground to like a higher elevation or from a high point to a low point. But if you do that, you have to run a quadratic equation. It's not crazy difficult. You know how to do the quadratic. It just takes a little bit of time, and I'd rather save us that headache if we don't have to. Plus, I can give you less information, and you can still do a lot more with it if I give you flat ground. So if I give you flat ground, and I give you the launch velocity of the projectile. Let's say, for example, here the launch velocity of the projectile is 20 meters per second. And let's say that I shoot it off, kick it off, whatever, at an angle of 70 degrees. 70 degrees is actually pretty steep. So I know this object's going to be in the air for a pretty long time. And I know that its y velocity is actually going to be greater than the x velocity here. Now, whenever we do all these problems, we always go about setting up the box. So let's do that real quick. For our box, we have an x direction, a y direction. Whoosh, whoosh, whoosh. Make your own sound effects at home, kids. We've got an initial velocity, final velocity, displacements in the x or the y direction, horizontal or vertical, accelerations and times. Whoosh, 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 whoosh. A few things we always know. Y acceleration due to gravity here on Earth is negative 9.8 meters per second squared. Acceleration in the x direction is 0 unless there's a crazy booster thing. Okay, and that's kind of what we know right now in the problem. We can get a little bit more if we take a look at this triangle being built here. This is a velocity triangle, not a distance triangle or a displacement triangle. And for this velocity triangle, what we can actually do is, since we know this side here is 20 meters per second, and we know with respect to an x-axis and a y-axis that it would form a 90 degrees. We happen to know that this angle here is 70 degrees. We can set up that this side is the opposite, this side is the hypotenuse, and we can play a little bit of SohCahToa here in order to solve this. What did I do? I'm sorry, that's not the hypotenuse. What was I doing? This is the hypotenuse. Ugh. And this is the adjacent side. Woof. Jeez, Buzz. Okay, so looking at our triangle here, if I want to find the opposite side, which is equal to the initial y velocity, I can say that, what is this? Go away, whatever that is. Shoot. I can say that the initial y velocity, let's write it like this. I can say that the sine of 70 degrees is equal to the initial y velocity over 20 meters per second. If I multiply each side by 20, the 20s go away, and 20 sine 70 equals the initial y velocity. If I shove that into my calculator, I get that the initial y velocity equals 18.79, I'm just going to round that up to 8 meters per second. And I can put that right up here in the box. 18.8 meters per second. Okay. If I want to find the x side, the adjacent, I can just say that 20 cosine of 70 equals the x velocity. This is both the initial and the final velocity, because in the x direction it doesn't speed up. And when I plug this into my calculator, I get a value of only 6.84. Let's just say 6.84 meters per second. Just like we said before, this value for the x velocity is less than the y velocity, simply because that angle's so steep, we were going more up than we are over. And we can just plug that into the x, 6.84, 6.84. They're the same. They're always going to be the same as long as this value is 0. Okay? Now, whenever we're looking at these problems, like we've already talked about, on the x side, we are looking to have 2 of 3 important features, where the velocity counts as an important feature, the displacement is an important feature, and the time is an important feature. If we have 2 of 3 of those, we can go ahead and use equation number 1, which is velocity equals a displacement divided by a time, v equals delta x over t, and we can solve for the other 2, or for the other 1, if we have 2 things. On the y side, though, we need to have 3 out of 5 of these 5 categories. We're always going to get 1 with gravity, but we need to have 3 of the other pieces there. Then we could use our best friend, final velocity equals initial velocity plus at, delta x equals 1/2 vf plus vi times time, displacement equals vt plus 1/2 at squared, or vf squared equals vi squared plus 2a delta x. Your pick. Have fun. But unfortunately, on the left side, we only have 1 quantity, the velocity. On the right side, we only have 2 quantities, not 3. And odds are you will find yourself in a scenario where you get stuck like this. You can't do anything. What you have to do is go back to our initial problem. What you have to realize here in this problem is that as this object is arcing through the air, you know a few things about it. You know that it is winding up at the same vertical height at which it started. And if it winds up at the same vertical height at which it started, that tells you that the displacement in the y direction here is equal to 0. You also know if it winds up at that same vertical height, the initial y velocity it had in the beginning up here, VIY, it's actually going to have that same y velocity down here, but just negative. So this is the final y velocity, which is just equal to the negative initial y velocity. So you actually know 2 things down in this piece right here. You know delta y could equal 0. We could put a 0 right here. And we also technically know that the final y velocity is negative 18.8. And then, hey, look at that. Now you know a whole bunch more for your triangle. You can go ahead and solve for time, bring it over because it's a shared quantity, and now look, you've got 2 out of 3 things. You can go ahead and solve for delta x if we are looking for how far is this object going. What you could also do, which is kind of fun, is you could split this problem in half, because we know these are symmetric around the center, even though that line is a terrible line I just drew. It's like I've never drawn a line before. If it's symmetric around the center, then what you know is that at the max height, all of the velocity is in the x direction. So you know up here, the final y velocity, if you were stopping this problem halfway, equals 0. What this allows you to do, allows you to use 18.8. It allows you to use 0 as the final y velocity, and then the acceleration of negative 9.8. That still gives you 1, 2, 3 things. You can still solve for a time with those 3 things and bring it over. The only exception is this time here is only half of the actual time you need. If you grab this time, it's only the halfway point. You need to double that time in order to grab the entire scope of the launch. So if we just kind of finish out this problem, doesn't matter which way you do it, we're going to do it with the way we've got right here, because we've got this nice box with a bunch of stuff. So I'm going to use equation number 3 from our best friend. Equation best 3 is VF equals VI plus AT. If we go ahead and solve this, we're going to get negative 18.8 equals positive 18.8 plus negative 9.8 times t. We will subtract the negative 18.8 over, and then we will divide by the negative 9.8. So what we're going to get is we're going to get negative 37.6 equals negative 9.8 t. Then when we divide, we're going to get negative 37.6 divided by negative 9.8 equals t. The negatives divide out. The time we get here, 37.6 divided by 9.8 equals 3.83 seconds. That's nice. We can go up and flunk that in the box. Both sides, like I said, because it transfers. And now looking at the box, hey, we've got one thing here, one thing here. That's a velocity and a time. I can go ahead and use equation number 1 to go solve for delta x. So if I want to go solve for delta x now, delta x simply equals a velocity in the x direction times time. That's going to equal 6. What was our velocity? 6.84 times 3.83. When we multiply those together, we get a total delta x of 26.2 meters. And that's how far the object actually shot in the x direction. If you wanted to, you could find the max height by taking either half of that time, 1.915, or finding it in this side of the problem. And then you could find a max height from that, knowing that the final velocity up here is 0. So there's a whole lot you could do in that problem, but it all starts by playing with SohCahToa in the beginning. We did SohCahToa in the beginning here. And then from there we recognized what we had in our box, and then we went and used appropriate equations. We used equation 3 to find time, then we used equation number 1 to solve for a displacement. So that's how we can go ahead for this problem. That's a C2 problem. You're launching something at an angle and it's landing at the same level ground. Like I said, if you did have an object going up to a higher point or something like that, you could still do this problem. What really changes is this delta y is no longer 0. So you can't say that this is just negative 18.8, and you can't just say this is 0. You would have to know the height of that cliff where you're shooting up or down from, and you could run a quadratic on it. But we won't be doing any of those in class, but maybe you'll see one in the future whenever you get to college or take an advanced course. Either way, this problem is finished. Sup, Liv?